On this lecture 2.2, focusing on rays of light, we will try our best to briefly motivate you what will be used later on, or we will be dealing more later on in chapters 6 concerning the propagation of light. So there, this ray description of light will be used more. And then finally in our chapter 10, focusing on geometrical optics and optical instrumentation, outlining us the basics, how we can understand behavior and performance of most of optical instruments out there. So there we will also take use of the concept of rays. So in essence, what we will be covering in this lecture is that we will go through the very basics quickly. We don't go into the mathematical details, we just show to you what we will go through in the course of what happens for a ray of light when it's propagating through for example, a piece of glass, such as a lens, and what happens at interfaces so that the light can either be refracted and bent during the process of being refracted at the interface or being reflected. So this is the brief motivation. I'll just now start the actual lecture. So rays of light, what they are and how they can be used, is that in essence, light, even though we know that it's a wave, it's electromagnetic radiation, many of the times light and its properties can really be understood in a more simple description than a wave description. So in other words, we do not always need to describe light as a propagating electromagnetic radiation, but rather we can use something simple, more simple description than this one. And in practice, if we can forget the wave nature of light, in essence, mathematically, what we would do is that we would let the wavelength lambda to tend to 0. In essence, we can neglect the diffraction of light. So light doesn't really diffract anymore, but rather just propagates straight through, and that's it. And in this case, we can most of the time really speak of geometrical optics, and this really helps treatment of propagation of light. So we can, in essence, we can just draw rays, so straight lines that are propagating through our system, through media, and that gives us an adequate description of things. And most of the time when we're thinking of optical instrumentation, for example, like how a spectrometer works, how binoculars work, how a telescope works, and so forth, how lenses behave, we can really understand the behavior of these kind of optical components or instruments even using this description. And this is nice, and we'll be learning more about this on the final chapter on geometrical optics. So this is a good thing to keep in mind, that even though electromagnetic radiation is a wave, it is like a wave-like radiation. Many of the times we do not need to focus on that, but rather we can use a simpler description. The nice thing about this is that we really have a simple and even graphical description for light, and that is using the description of rays. So basically, we can just, with a pen and paper, we can draw rays, and using them we can already understand and basic kind of rules that we can use to understand how light propagates. And these rays of light, in essence, if we would want to understand what happens in a more quantitative point of view, so what really happens for the radiation, in essence, the direction of ray tells us in which direction the energy of this radiation is going, is flowing, is propagating. So this is the kind of graphical description inside like a ray description, and physically it tells us of how much of energy is been propagating from point A to point B along the direction of the ray. So let's now take a kind of a more graphical example. So let's think of how a lens behaves and how an image formation process works. More on this later on in the geometrical optics chapter, but this is a screen. This is a figure from there. So the y0 basically tells us that we have an object here, and y0 is a parameter that tells us the black line here. This is a so-called optical axis that goes through the center of our instrument. Here, just a single piece of a lens. So y0 tells us a distance of our object point from the optical axis. And then if this if this point scatters light, or if it even radiates light in itself, for example, it could be a fluorescent molecule, then this light that is being emitted or scattered by the object, then it can be described as a bunch of rays, and they propagate through the system, and then the lens bends the rays accordingly, and then finally the rays may focus again and form an image. And these kind of processes can be understood quite well using the ray description of light. So we don't really need to deal with diffraction most of the time when we want to understand how lenses behave, but rather we can just use simple calculations and draw quite simple figures to understand what happens. And this is nice, and it really works quite well. And we have simple mathematical equations that tell us how we should draw these rays of light. And the kind of rule number one in this description is that unless there's some kind of obstacle, an interface, a change in the medium, rays propagate straight forward. So rays propagate straight in a homogeneous medium, in other words of saying. And homogeneous medium just means that it looks uniform in all directions. There's no kind of inhomogeneities inside. So just a kind of like a uniform looking media. And the main parameter that we can use to describe the properties of these kind of uniform parameter is the index of refraction, N, or refractive index. And this parameter tells us how light in essence refracts and reflects when the ray of light hits an interface. So index of refraction, it's defined as the speed of light inside the medium with respect to the speed of light in vacuum. More on that later during the propagation chapter. And in essence, this parameter then tells us that when this ray of light hits an interface, then how it refracts and how it reflects. And most of the time, we really don't need to understand the wave nature when we want to understand reflection and refraction processes. So we can really just look and draw rays of light at an interface of two optically different media, and then by just using simple laws that can be derived from the Maxwell's equations, we can understand what happens. And this is quite nice, because this gives us a possibility to understand quite complicated optical instrumentation based on just their geometrical features and what kind of optical interfaces they consist of. So here is an example more on this stuff on chapter 6. So we have now an interface between two optically different media. So the white media above could be vacuum, or in practice could be air, and the bluer medium there is a different medium, optically more dense medium, described by the refractive index of NT, and this could be, for example, a piece of glass, BK7 type of a glass or whatnot. And here Ni is the refractive index of the outside medium, and could be air, so the refractive index could be just unity. And now, if you know the refractive indices, what's the Ni and Nt, and if you know at which angle of incidence theta I the incident ray propagates, and here we have the wave vector here for the incident ray, we can really describe how it reflects and how it refracts at the medium, at the interface of the medium. So it's really these refractive indices, Ni and Nt, or N1 and N2, that are really completely enough to describe what happens for the ray of light at this interface. And like I said, part of the ray of light reflects, and it reflects into an angle of theta R meaning the reflection angle, and this of course is equal to the incident angle. More on this later. And then part of the ray of light refracts, and then this refraction angle theta t will be slightly different. And these processes happen at the same time, and they happen in a so-called plane of incidence. And this plane of incidence is being defined to be the plane where we have the surface normal, N here, and where we have the incident plane and the reflected plane and the transmitted incident ray, reflected ray, and the transmitted ray. So this is the refracted ray. And these, when we think of it, they form a plane of incidence. And then this is the interesting plane we should look at our parameters and then the description of reflection and refraction. But more on these concepts later. I just want to show here in our first chapter that what kind of topics we will be dealing with, so that you don't get spooked about the things and you already have a rough understanding of things that we will be covering in this course. So the angle between the incident ray and the surface normal, n, as you can see in the figure, this is known as the incidence angle of incidence, theta I, and the angle between the reflected ray and the surface normal, n. So the notation I use with my vectors is that I have the bar underneath my parameter, so that tells us that it's a vector, and I have a hat here denoting that this is a unit vector, so that the length of this vector is a unit. It's always a unit length of a vector. So the reflected angle or refraction angle is denoted with theta r, and these give us already a lot of information of what happens at the interface. And these angles, the angle of incidence and the angle of reflection, they are in fact equal, like I said, and we will be showing this later on why this is the case. But theta I equals theta r, and this is what happens. If you don't already know this, it's really worth remembering. And the connection now between the incidence angle theta I and the refraction angle theta t. So this connection is known as the Snell's law, and it can be easily derived by using many different means. And the Snell's law equals that the Ni, the refractive index of the outside upper medium, times the sine of theta I must be equal to Nt, the refractive index of the bulk medium into which ray of light is being refracted, times the sine of the theta t. So this is known as the Snell's law, and I will end my lecture here. If you do not know what's a Snell's law, now you know, and you should really memorize this, because this is really all that we need in essence to understand what happens at interfaces. And once we know what happens at a single simple interface, then we can also understand in principle how, for example, more complicated looking interfaces would look like. For example, how the surface of a lens would refract and reflect rays of light. So this is really the kind of starting point when we want to understand geometrical optics, the Snell's law. But I will stop here. Thank you for following me. And next we will have the final very short lecture on particles, so on the particle nature of light. So I thank you and enjoy your day.